Welcome to AP Biology, and today we are continuing enzymes.
All right. So today we're really going to focus on the physiology of how enzymes work. All right. Now, when we were talking about enzymes, right, we learned that an enzyme is a protein. And when we look at the function of a protein, the function of a protein is determined by its shape or its structure. We said ultimately the thing that determines the shape of an enzyme is going to be its sequence of amino acids. Now, when we look at an enzyme, it's a globular protein. It looks like a big ball. And there's one part of that enzyme that is in particular important, and that is the active site. Right? The active site is the region of the enzyme that the substrate is going to bind to. A substrate is just a reactant. All right, kind of two words for the same thing. It's all about the shape of the active site. Right? That active site has a very unique, specific shape that makes it extremely specific for the substrate that it works on. Right? We call this specificity lock and key. Right? Enzymes work through a lock and key mechanism, where the active site is the lock, the substrate is the key, and they fit together in a very specific way. Right? We talked about sucrase only acting on sucrose. If we keep the theme of digestive enzymes, you have lipase that only breaks down lipids, nucleases that only break down nucleic acids. All right? So every enzyme is extremely specific for the substrate that it acts on. Right? And it's really all about the shape of the active site. Now, we said in class that when the substrate goes into the active site, just like you see right here in this model, so here's your active site, here's your substrate. One thing that you can notice is that enzymes are massive molecules. So these guys are huge compared to the size of the substrates that are in our body. When the substrate goes into the active site, the enzyme is going to change shape. Right? And we always kind of describe it as giving the substrate a hug, right? And we call this induced fit. What we'll come to find in a minute is that this induced fit, when the enzyme kind of surrounds the substrate, it's going to put pressure, it's going to put strain on that substrate. And that's going to be when this chemical reaction is going to take place. When the substrate is in the active site, we call this the enzyme-substrate complex. Right? It's when the two are together, and this is when the enzyme is catalyzing the chemical reaction. Now, always remember that word catalyzing. Right? To catalyze a reaction means that it's speeding up the reaction, but it's not getting consumed by that reaction. So when this reaction is over, this enzyme will then go and catalyze more reactions. So what do the enzymes do? Remember, I've been telling you that there's really only two major chemical reactions that are occurring inside of you. What are they? What are your two chemical reactions? Go ahead, Paul. Good. Dehydration and hydrolysis, right? What is dehydration doing? Making bonds. Good. What's hydrolysis doing? Breaking bonds. That's all you're doing, right? You're either making bonds or breaking bonds. You're either building things or breaking them down, right? Well, it's the enzymes that are actually performing those chemical reactions. So if an enzyme is making a bond through dehydration, the enzyme is going to speed up this process by putting the substrates together. Now let's think about this, right? Say you have a beaker. Right, here's your beaker. Right? And you have two substrates. And you want to put these substrates together to form a bond. Do we all get the goal right here, right? Now let's say you had no enzyme, and these substrates are all moving around, right? You would have to wait until these substrates just randomly collided and formed the chemical bond, right? And that might take a really long time, and that might be a really slow process, right? Now, if I didn't have an enzyme, how might I make this process occur faster? How can I speed up chemical reactions? Yeah, heat it up, right? If you heat it up, these substrates are going to move faster, right? Does that make sense? And are more likely to come in contact with each other. So by heating up a chemical reaction, it's going to make that chemical reaction occur faster. Now, just to play the opposite, how can you slow down a chemical reaction? Make it cooler, right? Which would slow everything down. It's kind of how your refrigerators work, right? Think about what's happening to the food in your refrigerator. It's slowly decomposing, right? And decomposition is a chemical reaction. So by cooling it down, what are you doing to the rate of decomposition? You're slowing it down. And if you freeze it, then you're close to stopping, right? So heating it up makes it go faster. Cooling it down will make it go slower. So if we didn't have an enzyme, if you heated up this water, you can make this reaction occur faster. But in either case, you're still waiting on the random event of these two things coming together, right? Does that make sense? Now you throw an enzyme in the mix. So here's our enzyme, this big, massive molecule, right? And it has an active site, for these substrates. Something like that, right? So you put the enzyme in. The enzyme literally grabs onto the two substrates, right? And bam, puts them together. That's going to occur a heck of a lot faster than waiting for those two substrates to collide with each other. Do you see how much faster this enzyme is going to make this chemical reaction occur? It's literally grabbing onto the two substrates and bam, forcing them together, making that reaction go faster. It's performing the dehydration synthesis. Now, let's say we have the opposite reaction, right? Let's say you have hydrolysis taking place. So let's say this is our substrate. We have two markers put together, right? And we want to break the bond between the two markers. And let's say I'm the enzyme. So the substrate goes into the active site. And then the enzyme performs induced fit, right? And hugs it and puts strain on that bond, right? Is that bond now easier or harder to break? It's a lot easier, speeding up that chemical reaction. So enzymes are going to be the workers that are performing either the dehydration synthesis or the hydrolysis. They're going to physically put the two substrates together, making the bond, or it's going to put strain on the bond, physically breaking apart the two substrates. All right? So your enzymes are the workers in your body. And we're only performing two chemical reactions. We're either making bonds or breaking bonds. And it is the enzymes in your body that are going to be performing those actual chemical reactions, speeding them up. Make sense, everybody? We're okay? All right. I have a little animation that shows all of this taking place. Let's check it out. Right? See, he uses over and over again. We'll be talking about this next. See how it changes shape? Does that make sense to all of you? All right, sweet. It's a good little animation. Come on. All right. All right, so we're going to be focusing on environmental factors that affect the functioning of enzymes, right? So we're going to be looking at a few things. One, temperature and pH, and two, different chemicals that can affect your enzymes. So first, we have temperature and pH. Now, every single enzyme that there is in the world has an optimal temperature and an optimal pH that they work at. And this can vary from enzyme to enzyme. It could be different from enzyme to enzyme. Every enzyme has a specific temperature and it has a specific pH that it works at. I'll give you a really good example. If you look at all the enzymes in the human body, all of our enzymes, what temperature do you think all of our enzymes function best as? 98 degrees, right? Or in Celsius, it's 37 degrees Celsius. That is the optimal temperature for human enzymes. What happens to the functioning of our enzymes if our temperature increases? It goes down, right? What would happen to the functioning of our enzymes if our temperature decreases? Same thing, it goes down, right? So if you look at this diagram right here, here you see our optimal temperature is 98 degrees. If you fluctuate away from the 98 degrees in either direction, the functioning of that enzyme is going to go down. Now, here we have a special kind of bacteria. These are bacteria that live in hydrothermal vents that are extremely hot. And if you look at their optimal temperature is 77 degrees Celsius. That is more than double our body temperature. So you're looking at bacteria that survive at over 200 degrees Fahrenheit. That is their optimal temperature, right? These enzymes function at a much higher temperature than our enzymes function at. Same thing for pH. I love this example right here because it's both found within the human body. We have an enzyme within our stomach. It's an enzyme called pepsin. And pepsin is an enzyme responsible for breaking down proteins. It works at a pH of 2. You see in the diagram, it's actually a little bit less than 2, which is extremely what? Acidic. So this enzyme works in very, very acidic conditions. In your small intestines, you have an enzyme called trypsin. And trypsin works at a pH of 8, which is slightly what? Basic. So you have two enzymes, both within your digestive tract. One which is working at extremely acidic conditions, and one that works at basic conditions. Now, what happens if you change the temperature or the pH that you put an enzyme in, what can happen to that enzyme? It can denature, which is something that we learned about when we learned about proteins, right? When a protein denatures, when an enzyme denatures, what is happening to it? It's unfolding, it's unwrapping, right? So, in other words, if you change the temperature or you change the pH, all those bonds that hold the enzyme together, right? All of the hydrogen bonds that hold it together, they break, and that enzyme unravels. And if the enzyme unravels, is it working anymore? No. And what can no longer take place? That chemical reaction that it is catalyzing. So what were to happen if you took pepsin and put it in your small intestines? It would denature. What would happen if you took trypsin and put it in your stomach? It would denature. Right? So every enzyme works at an optimal temperature and an optimal pH. And if you change the temperature, you change the pH, you can denature the enzyme. And once that enzyme is denatured, it is functionally dead. And that chemical reaction can no longer take place. Tessa, let's say you get a fever. You get 105, 106, 107. First of all, at 103, 104, 105, you feel like complete garbage. Why do you feel like complete garbage? What is losing its functioning? Your enzymes. They're now in that down slope, right? And things within your body are not working at their optimal. Because now you've exceeded your optimal temperature, right? You hit 107, 108. What starts to happen? Well, what starts to happen to your enzymes? They are denaturing at that point. Once you hit about 108, your enzymes will start to denature. And once they denature, your chemical reactions are no longer occurring. You need chemical reactions to sustain life, and you're dead. All right? Now, does the same thing happen at lower temperatures? Do lower temperatures denature enzymes?
But they freeze them.
No. So enzymes will denature at high temperatures. They don't denature at low temperatures. Because at low temperatures, everything is just moving really what? Really slowly. So if you put enzymes in the refrigerator, are they going to denature in the refrigerator?
Freeze.
No. They're just going to be preserved. So they're just moving really slow. For example, I've had an enzyme since the summer that I've been storing in the refrigerator that we're going to use next week. It's called catalase, right? And it's not denaturing in the refrigerator, right? It's just moving really slow. Does that make sense? So if you make an enzyme acidic or basic, it's done. You cannot shift pH at all. But temperature, you have to be careful, right? Because temperature, if you increase it too much, will denature the enzyme. Question for you, and this is tricky for a lot of people. We said that as temperature increases, what happens to the rate of a chemical reaction? It goes faster, right? So here you have a chemical reaction. And as you heat it up, it goes faster, 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 zero. Because it goes faster and faster until what happens to that enzyme? It denatures. So usually, if you're looking at temperature and the rate of a chemical reaction, it goes like this. Goes up and then bam, right? Because as it gets hotter and hotter, the rate increases until the enzyme denatures and then it plummets. Does that make sense to all of you? Aaron, did you have a question? Yeah. No? Okay. So temperature and pH play a huge role in the functioning of your enzymes, right? And that's why your blood pH is so important. Anyone remember what our blood pH is? It's like 7.2, something like that, right? It's around neutral. And we said earlier in the year, if you want a really fast way to die, it would be to change the pH of your blood, right? Because your blood needs to be maintained at 7.2, 7.0. If your blood becomes in any way more acidic or in any way more basic, what happens to your enzymes? They denature, right? And that's part of the problem with things like diabetic ketoacidosis, right? Sometimes with diabetics, their blood can become too acidic. Yeah? Now, to prevent that from occurring, what system do we have within our blood? A buffering system. Do you remember we talked about the carbonic acid bicarbonate buffering system in the blood? Do we recall that? Right? And the job of a buffering system. Number one, do buffering systems make the solution neutral? No. They keep it where it's at. Right? So the buffering system within our blood keeps our blood at 7.2. That is extremely important because if pH of our blood changes, that is when our enzymes can denature. And you are your enzymes. You don't work without properly functioning enzymes. Are we good? All right. Now, this brings up something else really important. I love this slide. It's a weird conversation. It's an important conversation. Many enzymes in your body do not work properly unless they have something bound to it. These things that are helpers of your enzymes, they are called cofactors. Sometimes cofactors can be organic. Sometimes cofactors can be inorganic. Now, somebody should remember this. If something is organic, it means that it contains what?
Carbon.
It contains carbon. So a lot of inorganic cofactors are metals. They're minerals, like zinc and iron, right? These are cofactors. So many enzymes in the body do not work unless they have, let's say, zinc attached to them. We call zinc a cofactor. If the cofactor is organic, meaning containing carbon, we typically call it a coenzyme. So the way that we describe coenzymes and cofactors is that they are enzyme helpers, right? So this might be the enzyme. This might be its active site, right? And this enzyme does not work properly unless it has this coenzyme bound to it, right? So this coenzyme right here is essential for the functioning of this enzyme. Does that make sense to you? Right? And the only difference between a cofactor and a coenzyme is that coenzymes are organic, cofactors are not. Now, this is what I need to tell you. This is important. One of the most important things I tell you all year for your health. Don't write, just listen. Coenzymes are vitamins. Vitamins. All your life, people have been telling you to take your vitamins. Right? Vitamin A, vitamin B, vitamin C, vitamin E, vitamin D. They tell you to take zinc and all these different minerals that you get in your multivitamin, right? What has nobody ever told you? What any of these things do in your body? Right? People will tell you things like vitamin C is good for your immune system. They'll tell you vitamin A is good for your eyes. Right? They don't ever tell you why. Are vitamins macromolecules? No. When we talked about nutrition, we talked about carbs, lipids, proteins. We didn't talk at all about vitamins. Why do you take vitamins? Why are vitamins so important for you? Because many of your enzymes do not work unless they have a vitamin bound to it. Remember, you are your enzymes. Enzymes run every chemical reaction in your body. And literally everything that you do is a chemical reaction. Whether it's thinking, seeing, digesting, moving, every single thing happening inside of you is a chemical reaction. And every chemical reaction needs an enzyme. And enzymes need coenzymes or cofactors. So if you have a deficiency, if you are like a typical American and you are eating processed food that is void of vitamins and minerals, will your enzymes work properly? No. And your body will not be able to perform the vital functions that it needs to perform in order for you to work as a fully functional human being. This is why you need to take vitamins. Vitamins make your enzymes work. That's why vitamin A is good for eyesight. Because vitamin A is a coenzyme that is used with enzymes that are somehow involved in eyesight. They say vitamin C is good for your immune system. Vitamin C, and there's actually debate about that, vitamin C is a coenzyme that is used in enzymes that are function within the immune system. It all kind of makes sense, right? I'm not a supplement guy. I will never tell anybody to take protein powder and any of that garbage. I think it's a total waste of time, waste of money. There's one thing that every one of you should take. It is a good quality multivitamin. Not Centrum or some cheap garbage. Go buy a good multivitamin, right? Because it is essential to the functioning of all your enzymes. Right? And that's what's going to help your body to perform well. Right? It's all about your enzymes. So do that for me. All right?
You got it.
Now, I want to stop there. I went longer than I wanted to. Let's go over a question together. And I have to make a correction from yesterday. So let's end the video.